So for number 4, there are some very specific things we have to know. It's a sort of classic statistics problem, and let's jump right into it. So for number 4, they tell us that it is claimed that a new remedy cures 82% of the patients with a particular medical problem. This remedy is to be used by 115 patients, and it is assumed that the 82% claim is true. And so for part A, we need to find the probability that exactly 90 of these patients will be cured. So the first thing that it's a little bit hard to notice is understanding what we are dealing with, okay? When you enter the world of probability, okay, especially in the area of statistics, there's usually 3 things you can face at the AISL level. So on the one hand, you can sort of have like your classic probability. Okay, this is just, you have a bag of marbles, pick a red one or a blue one. Yeah, that's your classic probability problem. Where it can get a little bit more specific is if you're dealing with stuff like a normal distribution. Okay, then that is a whole other world. And the last thing that we need to engage upon, that we also often maybe forget, is the binomial distribution. And so what I suggest is to train your eye to notice what you are exactly dealing with, okay? The normal distribution, it's pretty evident because the exercise will tell you it's a normal distribution or not, okay? And classic probability, you will be dealing with classic probability if it's not binomial. I mean, that's like the order of events I suggest. Notice if it's a normal distribution because they would tell you. Then figure out if it's a binomial distribution, which is a little bit harder, and I'll tell you how. And if it's not either of those, then it has to be a classic probability problem. Yeah? How do you figure out if something is a binomial distribution or not? The big hint here is that for binomial, notice it's bi, so you still have something like, I don't know, bisexual. It's one or the other. Bi for 2. Bisector, I don't know, whatever, ¿cierto? So for a binomial distribution, it's sort of like you flip a coin. It's either heads or it's either tails. So a binomial distribution only has 2 scenarios. The other thing you can sort of realize is that the AI at the AISL level for a binomial distribution, they will be giving you 3 things, or at least half of them, right? They will be giving you trials, so amount of trials. They will be giving you a probability, and they will be giving you a X value. And all of this, I will explain it in a second. See? So binomial distribution is only if you have 2 scenarios, heads or tails. In this case, it's a binomial distribution because this remedy, it either cures you or it doesn't, period. So it's 2 scenarios. It cures you or it doesn't cure you. So in this case, we actually have a case of, binomial distribution. Okay, that is what we're dealing with. Now, one of the hints is that 2 scenarios thing that I mentioned, but the bigger hint, in my opinion, is this thing about trials, probability, and the X value. Okay, and this has to do with how you plug into your calculator. In your calculator, you will be plugging in trials, probability, and X value. So what is each thing? Well, trials, in this case, is 115. This remedy is being used on 115 patients, and you're checking to see how many times it works or not. So this will be your trials. This is the probability that it works. And the X value will depend on what they ask for. So for example, over here, if they're asking for exactly 90, then 90 is going to be your X value. And even reading ahead, they tell us for part B, the probability that at least 95 of these patients will be cured. Well, there is your X value again. So for the binomial distribution, the way it works is that they give you trials, they give you probability, and the X value is sort of like, okay, what's the probability that given these trials and given this probability, you get exactly 90? or you get at least 95. Okay, so the X value tends to be what changes, the trials and the probabilities stay the same. And so once you realize that that is the format for binomial distribution, it's going to be much easier for you to notice it, realize that it's there, etc. The other big hint is that here it says exactly, here it says at least, and I'm going to dig upon that in a second. Why is that a hint? Because your tools, the tools that you use for binomial distribution depend on exactly that. Guys, you have two main tools, okay? Because we're talking about a distribution, you will be pressing that distribution button in blue in your graphing calculator. So you press second vars, go to distribution, scroll all the way down until you find something that says binomial, and here it is. You have two main tools, binomial PDF, and binomial CDF. All right, and instead of jumping into what PDF means, what CDF means, and all that stuff, I'd rather have you memorize or write down somewhere, okay? That intuitively you want to remember binomial PDF with the word exactly. Well, binomial CDF, it's going to be sort of like, I want to say not exactly, but maybe that's not too friendly. So if PDF is an exact amount, yeah, if PDF is an exact amount, then CDF, we can consider it like a range of values. All right, that's a lot better. So binomial PDF is for an exact value, while CDF is for a range of values. See? So if you were to draw your binomial distribution that, I don't know, I think it's something like that. I don't recall perfectly well. It's a little bit like a normal distribution, but with a slant, with a skew, I should say. So PDF is like asking your distribution, like, okay, what's the probability of getting this guy there? See? That would be for PDF. The probability of this guy right here. What's the probability of landing that? Okay? While for CDF, it's a little more like, oh, from here to here, what's the probability of this? Okay, that's for CDF. Okay, visually, I will leave it like that. PDF is for an exact value, while CDF is for a range, right? All right, enough talking. So now if we jump into part A, it makes a lot more sense because we need to find the probability that exactly 90 of these patients will be cured. So clearly my trials is 115, my probability is 82%, and my X value is 90 because it's exactly 90. So do you use PDF or CDF? You use PDF because PDF is for an exact value. So you go to your calculator, you go to PDF, your trials is 115, your probability is 82. But notice this is 82%. So 82% as a decimal is 0.82. Quick reminder that 100% is 1, 50% is 0.5, and 5% is 0.05. If you memorize these three scenarios, you can convert any percent to a decimal, I assure you. So following this pattern here, you just gotta move the decimal a little bit. 82%, we're gonna leave it at 0.82. All right, it's important that you do that or else it's not gonna work. Your X value is 90 for exactly 90. PDF, because we're talking about exact value. Go ahead and press enter, bada bing, bada boom. That is your answer for part A. Quite literally, you will be putting, in order to show your work, you're gonna put binomial PDF, and then in parentheses, all that stuff. So 115, 0.82, and 90. All this is telling you in parentheses, by the way, all right, is that you went to binomial PDF, and the first thing it asks for, you put 115. The second thing it asks for, you put 0.82. And the third thing it asks for, you put 90. Which makes sense, because if we go back to binomial PDF, that's exactly what we did. Whoops. If we go back to binomial PDF, it's exactly what we did. First we put 115, then we put 0.82, then we put 90. That's what the parentheses is doing. And so write this out in order to get your method point, because whoever is grading you needs to know what you plugged into your calculator and how. Okay, so very important that you put this here. It is in the mark scheme as well. See, you have to write out what you did. All right, that's for your method point. And then the actual answer, we're going to leave it what we found earlier. I just plugged in the same thing twice. Who cares? 0.053 53251. 53251. All right, which is right here, right? If you were to do significant figures, if you'd like to, you gotta count 1, 2, 3, not including the zeros. Okay, not including the zeros. 1, 2, 3. Round it up or keep it the same. You keep it the same, so you can leave it as significant figures. 0.0535, which is exactly what they put right here. All right, so that is for part A. For part B, we need to find the probability that at least 95 of these patients will be cured. So immediately we are already talking about CDF for a range of values. Now, this guy online told you that PDF is for an exact value, CDF is for a range of values. We're talking about at least, so you're thinking, oh yeah, this is a binomial CDF, see? And so what half the world does is that they go to CDF, they put 115 for trials, they put their probability, and then they put the X value. Whoops, they put the X value. They go ahead and press enter. They put this under as their answer, and it's actually wrong. And this is because what we haven't talked about yet is how binomial CDF works. Okay? So the first thing that I need to mention is that much how I drew here, all right? CDF, so CDF, this is for CDF, ¿vale? So CDF works from left to right. And so technically what we did just now when we plugged in binomial CDF with an X value of 95, what we said was, okay, take our take our binomial distribution, which looks something like this, okay? Find, well, our maximum is 115, right? And our lowest has to be 0 because these are our trials. And then we said, okay, find wherever 95 is. Okay, so 95, let's say, is, I don't know, this isn't exactly drawn to scale, so who cares? But let's say that 95 is like here, okay? And so what the binomial CDF, what we just did, is that we found the probability of this right here. Now what the question is asking for, if we take a closer look, is at least 95 will be cured. So at least 95 cured. And what we drew here in pink was actually 95 or less cured. And that is because it's simply how binomial CDF works. Binomial CDF works from left to right. And there's a small percent of you that is staring at this problem, staring at this YouTube video saying, nah, my calculator has this fancy thing where I can choose whether it goes to the left or to the right. And I'm going to say, all right, cool. Most of the world doesn't have that. So if you have that, very good for you. That's very convenient. You need to understand that binomial CDF usually works left to right. If you have the option to say like, yo, take it from the right, even better, you can skip this next step, okay? But most of the people in the world will have to do this next step, which is basically, okay, since binomial CDF works from left to right, and I just got what is in pink, right? If I want to say at least 95 is cured, so that is 95 or above. Essentially, what you're trying to find is all the values that are 95 or above, including 95. ¿Cierto? So what you actually have to do is binomial CDF up until 94. So let's start off doing that. See? So we take binomial CDF and we say it until 94. Okay? So that's the first thing we're gonna do. We're gonna erase this ever so slightly, and we're gonna put the 94, I don't know, here. Okay? So now we found for 94, okay? And so for 94, you just discovered that the probability of this for 94 was 0.50896. So that was for 94. If you want to do like, it's just a little bit hard to explain. So CDF gave you, okay, CDF just gave me the probability of finding all my x values that were up until 94. See, because it reads it from left to right. And so if you want to find the other end of your distribution, the other end of the tail, what you actually have to do, okay, is 1 minus the left side, okay? You do 1 minus the left side. So if you do 1 minus the thing in green, in light green I mean, if you do 1 minus the thing in green, what you end up with is the part in dark green. Now why does this happen? Because way earlier what I told you was that in terms of percents, 1 equals 100%. So here what you're doing is that you're taking 100%, so you're taking the whole distribution, okay? So you take the whole distribution. When you put down 1, you take the whole distribution, the 100%, you subtracted the light green, so you have to end up with dark green. And dark green has to be greater than or equal to 95, okay? So we follow that procedure. We're going to do 1 minus what we got right there. And this is what gives you 95 or greater. See? So for part B, you have to do 1 minus that guy there. 1 minus binomial CDF of 115, 0.82, and 94, which gives you 0.491. Significant figures, you can leave it just like that. See? And if you go to the answer key, there it is, 0.491. Notice you have to do 1 minus that 94. See? So at least for me, from the visual aspect, it makes a lot more sense. Remember, you do 1 minus whatever, 1 minus the light green in order to get the dark green. See? And this is because binomial CDF reads it from left to right. So be very careful. When it says at least 95, it's 95 or above. Okay? So that's a small detail that becomes very relevant in this exercise. If you still don't believe me on the 1 minus thing, well, in your formula booklet, you actually have this thing here, complementary events. See? In the world of probability, you have to account for all scenarios. Complementary events is a little bit like the heads or tails. Okay, heads or tails. It either rains or it doesn't rain. It's either heads or it's tails. It either snows or it doesn't snow. And so those two probabilities added together have to equal 100%. And the same happens over here. ¿Cierto? Either the remedy works or it doesn't work. Either you have this side to the left of your distribution or this side to the right of your distribution. Yeah, that whole distribution got add up to 100%. ¿Vale? So, enough blah blah. That is for part B. For part C, it's fairly easy, but you do have to know one specific thing. So for part C, you need to find the variance in the possible number of patients that will be cured. Now this is actually extremely easy, but don't freak out, okay? Here's the point. The moment you read variance, this is a massive buzzword that should immediately get you thinking, okay? In the world of statistics, variance is a little bit like how much your data strays or how much your data moves around. Like, think about it that way, okay? Now, how do you calculate variance of a binomial distribution? Well, whenever you're asking yourself something as hard as that, it's probably in your formula booklet, okay? But also, you need to start accepting or understanding that variance is a buzzword, and variance is something that you need to start recognizing as something that is actually in your formula booklet, like for real, see? So, identify these buzzwords and identify these concepts that appear on problems and also in the formula booklet. So, eventually in topic 4, you will be finding the variance for a binomial distribution, which is right here. So the variance of a binomial distribution has to be, you need two things. You need n and you need p. N is simply going to be your trials, while p is going to be your probability. And I already mentioned earlier that trials was 115, so trials is 115, and probability is 0.82. So if you go ahead and plug that into the variance formula right here, you end up with 115 times 0.82 times 1 minus 0.82. So again, extremely easy problem, but you do have to realize that for variance, it's in your formula booklet. A lot of people enter the test thinking, I have my formula booklet, so I have all the formulas, like whatever. Nuh-uh, that's not good enough. You need to know what's in it, okay? Always study with it. Realize that it is an additional tool the day of the exam, okay? So there we go. We plug into the variance formula. My variance for binomial distribution has to be 16.974. If you think in terms of significant figures, you go 1, 2, 3, round it up or keep it the same. You do round it up, but if you round that up, you actually end up with 17. And so if we look at the answer over here, that's exactly what happens. You can leave it as 17. All right. So really easy 2 points. You just have to plug it into your formula from the formula booklet. Easy peasy lemon squeezy. Okay. So I guess the hard part there was realizing, that's actually my formula booklet. See, I'm sure a lot of people read this and they have no idea what to do. That is why you have to get familiar with buzzwords, with concepts that show up on your problems and in your formula booklet. That it. Study with the formula booklet. That is my main message. Study with the formula booklet. Yeah. Then they tell us for some reason that the probability that at least n patients will be cured is less than 30%, and to find, for part D, the least value of n. All right. So right now, this guy online told you that you have two main tools for binomial distribution. You have binomial PDF and binomial CDF. Now, in this context, we're talking about patients that will be cured is less than 30. So clearly, we're talking about a range. And so if we're talking about a range, it has to be CDF. All right. Now, how does CDF help from here? Well, you go ahead and open up your distribution thing. You go to binomial CDF, and it says at least n patients. And you can't really put a variable here because, I mean, that's not how it works, right? So the first thing we need to establish is that because they're asking for less than 30 and at least n will be cured, so at least n will be cured, and that has to be less than 30. Well, you did just plug in and at least 95, and how many of them got cured? Like around 49%, right? So that is already a big hint, okay? For these exercises, what I suggest, and I've seen this in mark schemes before, so you can trust me on this, you will probably be guessing and checking. Seriously, I'm not even kidding. So if you do a little bit of guessing and checking, you will get the least value of n in this context. Yeah? So, again, right here, you found the probability that at least 95 will be cured, which ended up being a little less than 50%, right? And so, what do we mean by guessing by checking? Well, if 94, if plugging in 1 minus binomial CDF of 94 gave you around 49%, then if I go back here, so for example, we can have, think about it this way. So if we do 1 minus this binomial CDF, see? We're established from part B that technically what's happening here is that this is giving you at least 95. So one above this x value. because CDF reads from left to right. See? So this is for curing at least 95. Yeah? So for curing at least 95, we got a percentage of around 49. See? But if you go ahead and increase 94 to, for example, 95, you end up with 39%. So this is decreasing, and eventually it's going to be less than 30. And this is what I mean by guessing and checking. That is, so you keep going, you change this 95 to 96, and because it reads from left to right, that means we're talking about at least 97. That's almost less than 30. Almost less than 30. So if we go ahead one more time and we change this to 97, again, this reads from left to right, so this is actually giving you at least 98. And what's the percentage of that? It's definitely less than 30. See? Right on this part here, which would be for 97, at least 97, it's a little more than 30%, and at least for 98, and for at least 98, it's less than 30. See? So the least value of n clearly has to be the last scenario that we did. See? So for guessing and checking, you can show that you did 1 minus binomial CDF of 115, 0.82, and 97. So technically what's happening here, if you want to get really fancy, is that you're doing 1 minus the probability, technically, ¿cierto? The probability that x was, it reads from left to right, so probability that x is less than or equal to 97. See? So that is actually going to end up as the probability of x being greater than or equal to 98. And the probability of that, from what you just plugged in and etc. and blah, 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 was 0.2217. So 0.22. So clearly less than 30. Now, you need to show, and here's the thing. Your guessing and checking is your method point. Okay, your guessing and checking is your method point, so you actually have to show that you were guessing and checking. ¿Vale? So this was like your final answer. Okay, yeah, 22. But you gotta show that you were guessing and checking a little bit. So just to get full credit, you should also write somewhere that you did 1 minus binomial CDF of 115, 0.82, and 96. So the one that was 1 before it. And that this gave you around 30, a little more than 30%. So this gave you 0.303. Okay? And it's very important that you do this because in the mark scheme, it actually says, of all the different methods, and for me, my favorite is method 2, okay, is that part of your method point is quite literally use the binomial CDF in the graphing display calculator for at least 2 different values of n greater than 90. All right, which is clearly, that's why we were spamming in the graphing calculator, but the person grading you doesn't know that. So you gotta show the person grading you, I did do that. You don't have to write them all. Writing 2 or 3 is good enough. And this right here is a very visually appealing answer, ¿cierto? You can see quite literally that I go from 96 to 97 until I go from a little more than 30% to a little less than 30%. So that would be for part D. So yes, guessing and checking here works. I've seen it in other mark schemes, and it's a suggested method, all right? And it's the one I suggest because for me it's the friendliest, pretty easy to understand, okay, whatever, see? Then they tell us that a clinic is interested to see if the mean recovery time, all right, so this is basically like a whole other problem. Yeah, so that's the first disclaimer. In paper 2, the cool thing about it, if anything, is that usually you have 2 problems melded into one. So all of this is its own exercise, and all of that is its own exercise. So all of this up here was for binomial distribution, and all of this down here clearly has to be for a t-test. Why do I mention this? The day of the test, if you have no idea how to do from parts A, B, C, and D, we'll take a good look at what happens on the next page, because maybe you can solve this, because this doesn't care about what happens in parts A, B, C, and D. Yes, it's part of the same exercise, but it's not part of the same like problem per se, you know? This is a t-test. You talk nothing about remedies or binomial distribution or anything like that. ¿Vale? I mean, yes, you talk about remedies because it follows the context, but you're not using anything from parts A, B, C, and D. You can literally skip to E, F, G, and H and solve it without doing anything beforehand, because you don't need anything from before. That's the message I'm trying to transmit to you. So the day of the test, if you face a problem and you're stuck on the first couple parts and it's paper 2, maybe skip ahead, because there's a whole other exercise waiting for you. Okay? Claw points wherever you can. Be on the lookout for that kind of stuff. So enough blah blah, let's get into it. We have that a clinic is interested to see if the mean recovery time, okay, so mean recovery time of their patients who tried the new remedy is less than that of their patients who continue with an older remedy. So the main thing that they're looking for is is if the new remedy is less than the older remedy. So new remedy less than older remedy. Okay. Actually, if I were to make it very, very fancy and say new remedy less than older remedy. The clinic randomly selects some of their patients and records their recovery time in days, and the results are shown in the table below. So right here, you have the first list, or the first table, which is for new remedy, right? So group N was for new remedy, and they recorded 1, 2, 3, 4, 5, 6, 7 people, right? So the first person took 12 days, the second person took 13, etc. And then for the old group, they had more people. They actually had 9 people that they tested. The first person took 17 days, the second one 11, etc. ¿Vale? So they tell us that the data is assumed to follow a normal distribution with the population variance, and that the population variance is the same for the two groups. This is a little more important than what you think, and that comes into play later, okay? The bigger thing here, though, that we will focus on is that it is a t-test, or that they use a t-test that compares the means of the two groups at a 10% significance level. So I know this is a lot of blah blah. I know that some of us are a little bit confused, so let's go piece by piece. The first thing is that a t-test, what it does is that it compares the means, quite literally. So whenever you're comparing means, you will be using a t-test, okay? And when he talks about a significance level, it's sort of like how much how rigorous your test is, okay? Let's stick with that idea for now. So a 10% significance level is how rigorous you want your test to be. Usually we talk about 10%, 5%, or 1%, okay? So that is something you compare with your p-value, but that will happen later. I'll explain that later. ¿Vale? For now, let's focus on part E. So for part E, you need to state the null. You need to state the null and the alternative hypotheses for this t-test. So for part E, the null is what they usually call H0, while the alternative is usually what they call H1. Now, for the null, what I need you to associate it to is that the null is usually simply like no change, while the alternative is going to be that there is a change, so yes change. Now, in this context, we're comparing means, right? So if null is no change, and we're saying, if the null is for no change and we're comparing means, the null we can leave it as same mean. So that means that between the old remedy and the new remedy, there is no difference, so it's going to be the same mean. There is no change. If there is a change, then you would say different means. All right, this is for the initial sort of intuition I need to give you. Now, this is clearly not like detailed enough. Like the IB wouldn't like this, because it's just saying that your null is the same mean and that your alternative is different means. Yes, you're getting the right idea, but you gotta be a little more specific than that. So for getting the full credit, you gotta be a little bit more specific. And so it's the same mean in what sense? So for the null, what we're gonna leave it as, like our official answer, everything from before was just for intuition. So our official answer for null, we would say something like You would say for H0 maybe that the mean recovery time between the old remedy and the new remedy are the same. Well, on the other hand, what you would say for H1, which is that there is a difference, you would say that the mean recovery time between the old remedy and the new remedy is not the same. And in this context, they're specifically looking for the new remedy being less than the new remedy having a recovery time that is less than the older remedy. So specifically here, you gotta go after what the experiment is being used for. So it's not only that they're not the same, it's actually that the mean recovery time of the new remedy is less than the recovery time of the old remedy. Dale? So in terms of words, that is how you can like sort of put it. The other way you can consider is that for H0, you would say that, well, this is gonna be my new remedy. I mean, sorry, I'm not explaining myself well. This first group is gonna be my first list, okay? Because it is the list of data. And so you will be talking about your first mean, right? So this is gonna be U1 for your mean, and list 2 will be giving you U2, which is your second mean, okay? So technically, if you wanted to put that in terms of math instead of words, although words are perfectly fine, you guys, if you're to put it in terms of math instead of words, you would say that for H0, so for H0, you can also say that the mean of your first one, right, of the new remedy is equal to the mean of your second remedy. Easy peasy. While for H1, if we're talking about the remedy of the new one being less than the recovery time of the old one, which is exactly what it says here, they're testing to see if the new remedy has a recovery time that is less than the old remedy. So that means that, well, new is U1, old is U2. So here you would say that the mean of U1 is less than the mean of U2. All right, so either of these scenarios that I'm now putting in pink will give you full credit. So you either put it like this, or you either put it in text like that. Either of them work. The main idea we need to stick to is that, as I mentioned earlier, the null, which is H0, basically talks about no change, while the alternative, which is H1, proposes that there is a change. Okay, and in this context, because we were talking about means, that is why we said that no change was the same mean, while yes change was different means. Now, in which way specifically depends on how the experiment is being conducted. In this case, different means in the sense that the new remedy has a lower time than the old remedy. All right, enough blah blah. That is for part E, and just so that you guys keep on trusting me, this is like the mathy way to put it, if you'd like to say, ¿cierto? But they also accept, notice, an equivalent statement in words, okay? So either of them works, whatever floats your boat, see? So that is for part E. Then for part F, they jump straight to the heart of the problem, find the p-value for this test. So part F, find the p-value for this test. How the heck do you do that? Yeah, this is simpler than what you think. The big thing here is that they're asking for a t-test. So you're gonna go to your calculator, go to, I think it was stat. So you go to stat because clearly this is a statistics problem. You go to tests because we're talking about a t-test. And two different t-tests will appear. You have like the normal t-test, you want to think about that? Think about it that way, like simply t-test. And then over here you have two sample t-test. ¿Vale? So you either have a t-test or a two sample t-test. If you press t-test by itself, you're going to see that it asks for a mean and it asks for a list 1. And that's it. But here we have two lists. We have the list of the group of the new remedy and the list of the group of the old remedy. So from here, it's not a t-test by itself, it's a two sample t-test because you have two samples. So we go ahead and press here. List 1 is L1, so this is going to be L1, all of this. All of that is going to be L1. And then list 2 has to be all of that. ¿Vale? So we have to make sure that we do that. list 1, list 2. Frequencies is if you have a frequency table somewhere. In this case, we don't. And over here, you guys, these 3 options, what it's technically doing is that it's asking for your alternative. It's asking for your alternative. So for the alternative, we are saying that the mean recovery of the new one is less than the mean recovery of the old one. And since we're calling U1 as new and U2 as old, this is my alternative. I need to express it right here. And so clearly I gotta press the one in the middle. All right. And then this last thing where it says pooled, we will be putting that it is pooled. Now, what the heck is pooled? What is happening? Pooled, for now, you just need to associate it to this statement right here, which they pretty much always give you. Okay. For the AISL level, in my experience, for pooled, you will always be putting yes. Okay, you don't have to exactly worry about it, but if you want to learn a little bit about it, pooled is essentially that the 2 samples that you're using, both of them follow normal distribution, but much more importantly for pooled, their variance is the same. That's the big thing about pooled. Their variance has to be the same between the 2 groups. If the variance is not the same between the two groups, you will be putting that it is not pooled. In my experience for AISL, you always put yes for pooled, but just if it ever comes up in some test or whatever, what matters here is that the variance is the same. Okay, so variance being same means that you have pooled. All right. That is what I want you to associate it to. That it? Now, the one thing I forgot to sort of show is that we're putting list 1 as all of this and list 2 as all of that. So where the heck do you do that? You gotta go to stat and then press edit, and here are the lists. Now I did get ahead of myself and put it earlier, so just double check that everything is correct, that it's aligned, etc. So here's list 1 right there, ¿cierto? And here's list 2 right over there. See? So enough blah blah. We go back to test, to sample t-test. Everything is okay. We go ahead and press calculate. We're pretty much never going to be drawing it because who cares? I mean, you can, but whatever. Go ahead and press calculate. See? You get a bunch of different values, and in this context, all they're asking for is for the p-value. See, there's a lot of stuff here. Don't get lost in the sauce. Cook only where you need to. The p-value equals 0.062. Yeah, we're going to leave it like that. So that would be the p-value for this test. It's the same one right here. All right, and then for part G, we need to state the conclusion for this test and give a reason for my answer. Now, I'm doing this on the fly. I'm actually not sure if this works, but it might help for explaining it. What if I press draw? What happens? I don't think I've ever done this actually. This might help for concluding. That's why I'm trying to draw it. Let's see. Oh, I'm drinking cold coffee right now. Not the best. But, gotta do what you gotta do, right? Oh, wow. That's actually pretty good. Not gonna lie. Yeah, so here, wow, calculator's gonna do a lot of stuff. Here I graphed my distribution, okay, and I did a 2-sample t-test, and I got a t-value and a p-value. Now the t-value and the p-value, what they both do is that they help you conclude the test. All right, how do they help you conclude the test? So here's the main idea that I need you to understand. Right now we have my binomial distribution that looks something like this. See? And we were talking about this is our alternative. See? And basically what this does is that you're going to be looking at the left side of your distribution. See? Just trust me on this. It's just going to be to explain what's happening. That it? Now, and this actually partly is also going to answer part H, so pay attention. That it? How do you conclude this? What is happening? What do the numbers mean, Mason? Mason, what do the numbers mean? So, in this context, okay, there are 2 main ways in which you can conclude your answer. One of them okay, is to compare. Okay, so for concluding, ¿vale? One method is to compare significance level to your p-value. Now, why do you compare significance level to your p-value? Because both of them are percents. Both of them are probabilities, okay? And the other way that you can sort of try to conclude is that you need to compare the critical value to your t-value. And why would you do this? Because technically both of these will be a sort of benchmark. Yeah, I'll explain both of these individually. See? So imagine you do this binomial distribution. It looks something like this. And let's say that your significance level, actually, let's apply it to the context. So your significance level, they tell you that it's 10%. ¿Vale? So that means that you're going to be drawing a line somewhere, let's say right here. And you're going to say like, okay, so this line, actually, no, it's the other way around. My bad. So for significance level, they tell you, so your significance level is 10%. So what you will do in theory is that you will count all of this area until you reach 10%. So you count the significance level until you reach 10%. ¿Vale? And so what the p-value does, so our p-value was just around, how much was it? 0.062 in percent, so 0.062, ¿cierto? If you were to pass it to a percent, it's actually 6.2%. ¿Vale? All you have to do is move this decimal place 2 times to the right. So the p-value we know is 6.2%. ¿Vale? So then over here, around there, ¿cierto? Is going to be my 6.2%. So what does the p-value mean? ¿Vale? This helps for part H, but really helps more for part G to understand how to conclude stuff. So what the p-value does is the following. Actually, the Marx team puts it in a really good way. So here they tell us that the p-value is basically, so this is for p-value. ¿Vale? The p-value is basically the probability of obtaining the results as those observed, given that the null hypothesis is true. So basically, if your null is true, the probability to observe what you're observing is your p-value. And so in this case, basically what's happening, okay, is that assuming that the null is true, and remember that the null was no change, so assuming that there's no change, assuming that the remedies don't matter, the probability to observe what I am observing is 6.2%. And remember, I did tell you that significance level was how rigorous your test is. And so essentially, what's happening here is that the experiment was conducted. They said that the significance level is 10%. So essentially what they're saying is that anything less than 10% is a little too extreme. And if it's a little too extreme, then it's a little bit too crazy. And if it's a little bit too crazy, then it's a little bit too unlikely. And that is when the null hypothesis stops working. Because the null is basically saying, there's no change like between one remedy or the other, it doesn't matter. But what you're observing has such a low probability of occurring that your null gotta be wrong. Okay, that's basically what it's saying. Your null has gotta be wrong because we were expecting, or we would be surprised, right, if there was a 10% chance of seeing what we're seeing, but we're seeing what we're seeing with a 6.2% chance. So that's a little bit too low. It's a little bit too extreme. And essentially, the null has got to be wrong, ¿cierto? And so you compare the significance level to the p-value because they're both percents. They're both probabilities. P-value is less than significance level. And now this is for part G. So p-value being less than significance level means that the values are too extreme. Okay, so value is too extreme, assuming that null is true, right? And so if the p-value is less than the significance value, the values ended up being too extreme, which means that the null is wrong. So if the null is wrong, you reject HO or H0. See? Because the values are too extreme, you reject HO. So for part G, the conclusion of your test is that you reject HO, and the reason for your answer is exactly what I'm putting now in red. That is your justification, which is literally what they do in the mark scheme. See? They compare, right here, they're comparing the p-value to the significance level. Okay? So I guess if you want like full credit, you would have to plug in the numbers here and say, okay, this is 6.2% being less than that 10%. Okay, so clearly you have to reject HO. That is the first way to conclude using significance level with p-value. Essentially, you're comparing percents, comparing probabilities. That it? So that was for comparing probabilities, what's in pink and what's in black. Technically, not in this case. I mean, I already finished G and H. You can go, you can have a nice day. But just so you know, I did say there are two ways to conclude. Either comparing percents and probabilities using significance level and p-value, or comparing critical value to t-value. That's also why my calculator over here gave me a t-value there and a p-value here. It's telling me, dude, conclude your answer either using the percents or using the benchmark. ¿Vale? And here's the main idea. When the exercise talked about the significance level of 10%, if you draw in that 10% here, ¿cierto? Well, it's gonna stop somewhere. And so wherever it stops, right here is where you can actually put your critical value. And so the other way to solve this is that at 10% significance level, you discover a critical value, ¿cierto? So right where the 10% stops is where your critical value is going to be, and this is your benchmark. So anything to the left of your critical value is going to be too extreme. And so the other way to conclude is that if your t-value is, well, in this context, we're talking about to the left. So if the t-value is less than the critical value, ¿cierto? Again, you would be rejecting, right? In other cases, it might be that the t-value is greater than the critical value if we're talking about, I don't know, this side of the test, ¿cierto? So if your critical value happened to be over here, then you would have to be considering some value that ends up over there, see? Point is, you either compare the probabilities or you compare the benchmarks. The probability is what gives you the benchmark is what gives you the probability. Vice versa, it works the same. In either case, you are always exploring, and this is the main idea of the p-value, if your values are too extreme. So again, p-value is assuming that your null is true, and if the probability of seeing what you're seeing is too low, it's too crazy, it's too extreme, you reject the null. Okay, so reject the null. All right, ladies and gentlemen, enough blah blah. I hope I cleared up one or two doubts. That would be for number 4.